Welcome back to Physics 1053 at Daytona State College. This is Dr. Michael Olson. We've been in the middle of Chapter 9, talking about static equilibrium. In this video, we'll complete Chapter 9, doing the second half of the chapter, talking about balance and elasticity. We'll begin by talking about balance, what we mean by stable, unstable, and neutral equilibrium. And we'll discuss elasticity. We'll define stress and strain, as well as take a look at Hooke's law, which is a law concerning forces in springs. Then we'll define Young's modulus, shear modulus, and bulk modulus, which are the relationship between the stress and the strain. Okay, so to begin, recall that in the first half of Chapter 9, we talked about how to have true stability or equilibrium. We need to have the sum of the forces and the sum of the torques both equal to 0. So here, our example on the left, we have a ball that is just hanging, gravity's pulling it down, tension's pulling it up, equally balanced, therefore it is in complete equilibrium. All the forces add up to 0. But if we take this ball and pull it to the side, gravity is still down, but now tension's at an angle. The y component of tension will completely cancel out, well, almost completely cancel out with gravity, but there's also now an x component to tension as well. As a result, you're going to have a net force. In other words, sum of the forces is no longer equal to 0. When this happens, when an object is displaced from its equilibrium, one of three things can happen. In this picture, we have a displacement from equilibrium, and the net force is going to bring it back to its equilibrium position. This is said to be a stable equilibrium, where the force always brings it back to its equilibrium position. Now, if you have, say, a pencil balanced on its tip, if it's perfectly balanced, then the gravity is going to perfectly balance the normal force, and it will be in equilibrium. But this time, if you displace it from equilibrium, the gravity is going to pull it down, normal force is pushing up, sum of the forces still equals 0, but now the sum of torques is not equal to 0. There is a different torque because, the torque from the normal force is 0, but there is a torque due to gravity. And so that's going to pull it away from equilibrium, and any force that pulls an object away from that equilibrium is said to be unstable equilibrium. The third type is what we call neutral equilibrium. Let me explain it this way. Imagine you have a refrigerator whose center of gravity is right in the center of the refrigerator, right above the normal force. This would be its equilibrium position. If you tip it up a little ways, you have the center of gravity to the left of your pivot point where the normal force is applied. That's going to exert a counterclockwise torque, bringing it back to equilibrium. So here in B we have we have a stable equilibrium because it brings it back to its original position. In C, however, we've tipped it a little too far. The center of gravity is pulling it in a clockwise manner. It's going to tip it further away from that initial equilibrium point. So this would be our unstable equilibrium example. Now, 2 points here. First is note that as soon as this refrigerator falls, reaches the ground again, that's going to create its new stable equilibrium position. So whenever you have an unstable equilibrium, it'll just create a new stable equilibrium later on. That's not the critical point. The critical point is what happens right in between B and C. What would happen if the center of gravity were right over the corner that's on the ground, the pivot point? If that center of gravity was exactly over the pivot point, then there would be no torques, and sum of the forces would equal 0. We would be in equilibrium, static equilibrium. This one we would call neutral equilibrium because it would be perfectly balanced. It's stable. It's not stable. It's static. It's not moving. But it's any movement one way or another, it will become either stable or unstable. All right, let's take a look at Hooke's law. Hooke's law talks about how an object can stretch or compress and relate the force of stretching the object to the length that it stretches. So imagine you have a pole here that has some length L. You hook a mass up to it, that's going to stretch the object some distance delta L. Well, that distance delta L is directly proportional to the force being applied. And in fact, the force is going to equal just some constant times delta L. That constant is what we refer to as a spring constant. We'll talk more about springs in chapter 11. Until then, just know that this K is a property of the material itself. It's, in this case, it would be a property of this rod. How wide is the rod? What's the strength of the rod? And those properties are defined in what we'll define in a second as stress and strain. Now, when an object stretches, it will always return back to its original shape. So you take a spring, you stretch it, it will snap right back to its relaxed position. We call this elasticity. So anytime, if we draw a diagram of the force applied to an object to the distance it stretched, then it will, remember, force and length, delta L, are directly proportional. That means that it has a constant slope, and that slope would be our spring constant K. So if you stretch it some distance, the force will pull it back and it'll snap right back to its original position. But there comes a point where you reach what's called an elastic limit. In other words, if you go beyond this elastic limit, you will permanently deform the object that's being stretched. You can imagine, say, a slinky. Take a slinky and stretch it, pull it out too far. What happens? It stays stretched out. It will never go back to its coiled position. Once that happens, it no longer becomes elastic, or it is no longer elastic, it becomes plastic. Plastic would be this region here where it has elastic type properties, but it doesn't ever return to its original shape, and the spring constant is no longer constant. You keep stretching this plastic, it'll come to some point where it'll actually break. It can no longer withstand the stress or the strain put on the put on it, so it will break. Okay, so to define how much stretching an object can endure, we need to define stress and strain. Now, this is important because the property of the material depends on a number of things, including the cross-sectional area of the material and the length, the initial length of the material. So we're going to define stress as the amount of force applied to your elastic object divided by the cross-sectional area of the object, so force per area. That is our stress. Our strain would then be how much the object changes length compared to its original length, so delta L over L naught. Now, this ratio between stress and strain, the ratio between stress and strain is what we call Young's modulus. And it is just a comparison of the stress, force per unit area, to the strain, change in length over initial length. That becomes our Young's modulus, E. We can slightly rearrange this equation and solve for the change in length of an object. So if you stretch an object, its change in length will be 1 over Young's modulus, which is defined by the material itself, times the force per unit area, times the initial length. Now, in your textbook, in Chapter 9, there is a table that shows the Young's modulus for a variety of materials, for iron, for copper, for plastic, for many different other materials. Okay, so far we've been talking about one-dimensional stretching. So we just stretch it in one dimension, either X, Y, or Z, one of the three dimensions. These are tensile stresses based on tension. They tend to stretch an object, as we have been talking about. But we also have to recognize the opposite. Instead of stretching, what if we compress and push it towards, push it inwards instead of stretch it outwards? For example, here in this picture, you have these columns in this building are under compression as the roof is resting on the columns, pushing them down. This follows the exact same principle as the stretching that we just talked about. Exact same. The only difference is that your change in length is now going to be negative because you lose length, which means you're going to have a negative force as well. So other than that, it is exactly the same. Use the exact same equation. Now that was a one-dimensional example. We can look at changing an object's shape in two dimensions. So for example, imagine you have a cube and you shear it. In other words, you push a force on the top in one direction and an opposite force on the bottom. That's going to cause the top to shift by some distance delta L. Now, we can measure that length delta L using the exact same formula we did before. 1 over G, where G is now defined as the shear modulus, also defined in that table I mentioned a minute ago, times the force over area, where area is the surface on the top, times the initial length, which would be the height of your object. Now we can also do this in three dimensions. But in this case, it is a little different because if you apply a force in three dimensions, it's not going to increase in length, it's going to decrease. And since we're dealing with three dimensions, it's not length, it is volume. So we get the relationship that the change in volume over the initial volume is going to be the negative of 1 over B, which is the bulk modulus, times the change in pressure. In Chapter 10, we'll define pressure as force over area, so really we're talking the same equation here. So again, this is the exact same equation as we've done with Young's modulus and shear modulus. The only difference is as you increase the pressure or the force, you're going to decrease the volume, so you need that negative in there. So that gives us Young's modulus in one dimension, shear modulus in two dimensions, and the bulk modulus in three dimensions. So what's the overall point of this video? First of all, we talked about balance and the definitions of stable, unstable, and neutral equilibrium. But we also talked about how materials can be under compression or tension, which would be one-dimensional stretching. We also talked about shear stresses, which is a two-dimensional change in shape, and as well as bulk modulus or bulk stress changes in volume, 3 dimensions. We also saw that if you have an object, you could stretch it and it will return back to its shape. If you stretch it too much, it will lose its shape. It becomes a plastic instead of elastic. And then if you stretch it even further than that, it will exceed its elastic limit. That's when it becomes a plastic. Increase that stress a little more and it will eventually fracture and break. All right, this video completes Chapter 9. So tune in next time for the next video. And until then, we will see you soon.